Okay, so we are going to continue looking at differential equations, uh, and this segment of differential equations that we look at is just simply focusing on the Bernoulli equations. So before I continue, in case you're new to the channel, consider subscribing, ring the notification bell, so that each and every time we upload new content, you'll be notified. Okay. So when it comes to Bernoulli's equation, we are going to briefly talk about the theory segment of it. Then we'll dive into answering some questions. Um, then yeah. So what it is that when it comes to the Bernoulli equation, it's just a differential equation. I would say it's a differential equation that is in the form dy dx plus p of x multiplied by y is equals to q of x um, multiplied by y to the power n. So in this case, p and q, they are just functions of x. All right, then this y that I have here is the dependent variable that we have. And one thing that we have to note here is that the the equation like is given in this form, and the form in which it's given, where if we say or when we say n is not supposed to be equals to 1 in this case, uh, this turns out to be a non-linear differential equation. So our main goal is to make it linear so that we can use the integrating factor method to determine the solution of this particular differential equation. So then how do we go about it? So the first thing that we have to take note is that or what we have to do is to change the dependent variable from y to some other letter that you can use as a variable. So in this case, I'm going to change from y. Okay, instead of me using y, I'm going to use z. All right, I'm going to use z. So and it will be such that z will be equals to the y, which is the dependent variable that I have, that is raised to the power 1 minus what, 1 minus n there. Okay, so what it is that the fact that I'm changing my dependent variable, which is y, it also tells that I need to change my dy dx, meaning I need to be using dz dx. So the question is that how do I come up with the dz dx? It's just a matter of you differentiating what you have there, okay, with respect to x. Okay, so what it is that this part, when you differentiate what you have here with respect to x, what you're going to get is dz dx will be equals to, of course, this power is going to drop. You're going to have your 1 minus n, okay, uh, multiplied by y. Then you're going to reduce the power by 1, where you're going to have like 1 minus n minus 1. But remember to say here, this will be multiplied by what, dy what, dy dx. It's more like you this is like implicit. It has to do with you using implicit derivatives kind of stuff. So this of course is going to give you dz dx to be equals to 1 minus n. Okay, giving you 1 minus n multiplied by y. This one and that one goes, you get negative n by what, dy dx. So remember to say we are substituting where we have dy dx, we're substituting with what, um, it's more like we need to make I need to make my dy dx the subject of the formula, so that I see what I'm going to get. So this is going to be dy dx will be equals to, here we just simply divide both sides by what, both sides by what you have here. And what we are going to get is that we are going to get 1 over 1 minus n to the power y minus n multiplied by what, dz dz dx. And you observe to say, here I have to the power negative n. I can make that a positive by saying, okay, my dy dx will be equals to y to the power n divided by 1 minus n. Okay, then no, okay, yeah, like that. So I have written my I now have my dy dx in terms of dz dx. So it's just a matter of now what? It's just a matter of substituting. But before I do that, I need to multiply this that differential, that Bernoulli equation there that I have, that's given in that form, by 1 over I need to multiply it by I need to multiply it by 1 over y to the power n. Okay, so you need to multiply it by 1 over y to the power n, of which if you multiply by dy dx, that will just give you what? Dy dx there plus. Okay, so at this point you're going to have p as a function of x. You're going to have y. We have multiplied by 1 over y to the power n, which is that. But you observe to say, since the bases are the same, instead of saying y divided by n to the power, I mean, instead of saying y divided by y to the power n, I'm going to write this as 1 minus n. Okay, which is equals to q of x. If you multiply this by 1 over y to the power n, you're going to get just q of x there. So remember, we are changing this. What we have here is simply what? Is simply a z. So this is just simply 1 over y to the power n dy dx plus what? Plus p of x as a function. So here you're going to have z is equals to what? Is equals to q of what? Q of x. So maybe, um yeah, we are very close into having it in a certain form that we want it to be. So where I have dy dx here, I'm going to substitute with what my dy dx here is, what we have found. So it's like 1 over y to the power 1. Okay, so we have y to the power n here divided by 1 minus n. We close by dz dx plus p of x z is equals to q of x, like that. Okay, so now we can simplify this a little bit. uh, don't need that. So now this turns out to be, you observe to say that goes and that can go. You simply have 1 over 1 minus n, okay, multiplied by dz dx plus uh, p of x multiplied by z is equals to q of x, and that's what you have right there. So now the form in which we have it right now, it would be easy for us to use the integrating factor method, to come up with a solution, okay, of that the particular differential equation. So whatever equation that you're given, just write it in this form. Okay, then you can go ahead and uh, determine the solution for that particular differential equation. Okay, so now let's try to look at some examples and see how we can work this out. Okay, so let's try to look at this example. Let's say we have dy dx plus 3x squared by y is equals to x squared y to the power 3 there. Okay, so what you observe in this case is that at this point, what you have here, that's your n. Okay, that's your n, because this is q of x, this is p of x, then you have that y that you're going to change to be z. So this is what, at this point, that's where I get my n from. So here I'm going to say my n is equals to what? I've determined that my n is equals to 3. So remember to say, we're going to say our z is going to be equals to y to the power 1 minus n. So this would be like y 1 minus 3 will be equals to y to the power negative what? Negative 2. Okay, which is simply 1 over y to the power 2 there. Okay, so keep in mind, we said this our dy dx, we're going to say our dy dx will be equals to 1 over um, we said it was going to be equals to 1 over 1 minus n multiplied by dz dx. That's what you're going to that's what you're going to change it to. Okay, so now what you observe right now is that your um, at this point, let me write it in this way. Okay, so you're going to, I'm just going to substitute in advance at this point, then I'm going to have to take it that side. So I have my 1 over 1 minus my n is a 3. I have dz dx, so this gives me negative 1 over 2 dz dx. I'm going to bring it here. I have negative 1 over 2 dz dx instead of dy dx, because that is what my dy dx is equals to. Is equals to what? It's equals to that there. Okay, then I'll say plus what? Um Plus 3x squared. So at this point, you know that your y, your this has been changed to what? That has been changed to z. Okay, so it's just more like I'm putting a z there is equals to. Okay, that will be x squared. So this, it that goes away. At which point does it go away? It's the point at which I multiply everything by 1 over what? 1 over y to the power n, of which my n is what? Is the power 3. So you multiply that and that goes. So we don't have to worry about that part anymore. Okay, so now looking at the way it is, we can now easily come up with what? We can now easily use the integrating factor method to come up with a solution. So in this case, um, what it is that I need to leave this as what? As dz dx, as a positive, not as a negative. And remember to say it's like by a fraction multiplied by 1 over 2 there. Okay, it's multiplied by 1 over 2. So it's more like at this point you have a 1 and you also have a 1 there. It so happens that uh, for these two, it so happens that your common denominator is a 2, whereby you're going to multiply this by 2. Okay, then this by 1, then you have like this is going to be a 6, but with a 2 on the denominator for everything. But I won't have to waste my time with a 2, because I know I can multiply the 2 by what? By what I have this side. All right, and once again you can or maybe to simplify this, to write this in a very simple way for everyone to understand, I'm just going to multiply everything by negative 2, so that I get rid of that negative 1 over 2 there. Okay, so by doing so, I'm going to have dz dx minus 6x to the second z there. Okay, then that is going to be equals to negative 2x to the second, like that. Okay, so now I can use the integrating factor method. Okay, so which I know that, okay, now my p of x is quite clear that it's equals to what? It's equals to negative 6 x squared. So it's very important that you come up with the correct format, because you might get something that is wrong if you don't do things right. Okay, so what about your q of x? Your q of x is nothing but negative 2x squared. Then remember to say, to find the integrating factor, we're going to say it is e raised to the power um, the integral of p of x dx. What is this now? So here, where this p of x, I'm going to put what I have there, but I'm going to put my negative 6 outside. Then I have x squared dx. This turns out to be negative 6 multiplied by x to the power 3 divided by what? Divided by 3. Okay, this hence reduces to 3 there 1, 3 there 2. It's e to the power negative 2 x to the power 3. Okay, e to the power negative 2 x to the power 3. That's what we have. Then we can, like, since it's the power is the negative, we can just say it's 1 divided by what? 1 divided by e to the power 2x to the power 3. That's what we have as the integrating factor there. Okay, so now what it is that to come up with a solution, remember to say I am no longer dealing with y, and I'm going to say to come up with my solution, it will be like z will be equals to the integral of the integral of the integrating factor that we have found which is simply 1 over e to the power 2x to the power 3. I'll multiply by the function q of x. So remember to say my q of x is negative 2x squared. I'll just put, in fact, let me just put the negative 2 outside so that it becomes negative 2, like that. Then I'm going to have something like uh, my function q of x is simply x squared. That's what I have. Then I'm multiplying by the integrating factor that I found, which is that one. But maybe I'll use this one so that everything is like, I'll have everything on, like, I'll have it as a negative. That is like e. Uh, then I have 2x minus 2x to the power 3 dx there. Okay, so what it is there is that at the point at which we have reached right now, it's just a choice that you have to make to say, okay, which method am I going to use to come up with what, to come up with a solution. Like, how are you going to integrate? That is literally up to you. Okay, so now I can use u substitution here. Okay, I'm going to let my u be equals to, try to use a different color. I'm going to let my u b equals to minus 2x to the power 3, of which I observe to say is very easy for me to cancel out, because if I differentiate this, like the first derivative is going to be have it at some point. It's going to have like x to the second, and I have x to the second here, of which it gives me a hint to say, okay, I'm able to do the cancelling out there. Okay, so meaning u prime or du will be equals to negative 6x squared dx, of which you can say your dx is nothing but minus uh, du over negative, not negative, I've already written the negative, over 6x squared, like that. So I can come back here and say, okay, my z will be equals to negative 2. I have x squared multiplied by e to the u. My dx is nothing but negative du over 6x squared. That and that goes. So the negative and that negative goes. So 2 here, 1, 2 here, 3. This turns out to be 1 over 3. Okay, to be 1 over 3 multiplied by the integral of e to the u du, of which this is just something like we are still going to get 1 over 3 e to the u plus what, plus a constant. Okay, that's what we have as our z, but it's not really the final solution anyway. But we are close. So we have determined that our z um, is equals to 1 over 3. Okay, 1 over 3 e to the u plus c. And for convenience's sake, instead of me still continuing using u there, I'm going to use what my u is, because I had to let my u to be equals to negative 2x to the power 3. So I'm saying plus what, plus c. So to find the final solutions, the final solution to that one, there are two things that I have to do. I have to take this back to what, to y, to what y is initially, and I also have to multiply it by the integrating factor. So now I know that my z is equals to what, is equals to that 1 over y squared. That's what I have as my z. Okay, so meaning here, instead of me using z, I'm going to use 1 over y squared. I'm just getting it from this. Our z was equals to that, but because we know what our n is, it gave us that. Okay, then we are also going to multiply that by what, by the integrating factor, which is simply 1 over, I'll use the positive one, that is like e to the power 2x to the power 3 is equals to 1 over 3 um, 1 over 3 in fact, let me write this as a positive, with a positive power, 1 over 3e to the power 2x to the power 3 plus c. Okay, then at this point I'm going to do the cross multiplication. uh, this one I'll multiply by the numerator of everything here, or we are multiplying everything by e to the power 2x to the power 3. Okay, which gives us 1 over y squared is equals to, you're going to remain with 1 over 3 here because that and that are going to cancel out, so you just remain with plus e to the power 2x to the power 3 c, like that. But okay, this is like the general solution, but if you want you can write it in terms of y. um, that's literally up to you. I'll leave that for you to finish. Okay, all right. So now let's try to see if we can do some more examples, or maybe I can end on this one in this tutorial for more examples under Bernoulli equation. uh, Make sure you watch the next video. Yeah, otherwise thank you very much for watching.